This is part 2 of the video of lesson 3 of chapter 10. It starts off asking you to graph r equals 2 plus 2 cosine theta, which we did in the first unit, and it comes out looking like this cardioid. It's important to know that the domain is 0 to 2 pi. Also be able to graph this in your calculator, changing the mode to polar. And if you were to graph this from 0 to pi only, you would only get half of the cardioid. And that would be an indication to you if you needed to know what the domain was for a full revolution and graphed it only to pi, you would come to learn, oh, that's only half. Then you would try 2 pi to see that it completes the object. So what we're going to do here now, we desire to find dy dx, the concept that doesn't change. Dy dx, no matter if we're in parametric, Cartesian, polar, it always is the slope of the tangent to the curve at any point. So it could be the slope of this tangent, if that were actually tangent, slope of this tangent, slope of this tangent. So dy dx always represents the slope of the tangent to the curve. So how do we find this? Well, you probably are thinking dy d theta over dx d theta, very similar to the parametric. Here, however, we don't know what y is. Well, we actually do. Y, so the derivative of y, and y is r sine of theta with respect to theta. And the x is the derivative of r, cosine of theta with respect to theta. And that's great, but r is actually the function that is given. So this becomes the derivative of r, which is 2 plus 2 cosine theta, times sine theta with respect to theta, over the derivative of 2 plus 2 cosine theta times the cosine of theta with respect to theta. This requires us to use the product rule. So I'm going to draw an arrow over here so we can continue. We have the first term times the derivative of the second plus the second term times the derivative of the first, which is negative 2 sine theta. In the denominator, first term times the derivative of the second, negative sine theta, plus second term times the derivative of the first. And that's it. That is the derivative of y with respect to x in terms of theta. We can leave it like that. So if the question asked us to find dy dx at, let's say, theta equals pi over 4, let's make that pi over 2 so it's not so ugly. Then I would plug theta is pi over 2 in for this, and you get something along the lines of negative 2 over negative 2. Try it out, verify that, and it comes out to be 1. So that tells me when theta is pi over 2, the slope of the tangent is 1. And that looks true here. As bad as that hard is, and as hard it is to draw a tangent on this computer, you see that that slope does in fact look like 1. Now we have to find the area inside. This will be 4C. We have to find the area inside it. So this is developed. The area of a sector of a circle, here's a circle, here's a circle, here's theta, here's r, and you have to find the area of the sector. Well, it's pretty easy to verify that the area of a sector is 1/2 the radius squared times theta. So now we're going to sum up sectors. That's the way this works. So picture if we had a circle sector here, and then a circle sector here, and we had a whole bunch of circle sectors added together, then those circle sectors would approximate the area. So we can say that the area is approximately the sum of 1/2 r squared change in theta. So the area actually equals then an infinite sum from, we say theta equals alpha to theta equals beta, 1/2 r squared d theta. So that's the formula we're going to use to find the area inside a polar curve. And also you can see how important it is to know what the domain is to give one complete revolution. So specifically here, the area is the integral from 0 to 2 pi, going around like this, going around in that fashion from the pole to the curve, going out a distance of r. This is going to be 1/2 r, which is 2 plus 2 cosine of theta squared d theta. Please calculate that, evaluate that on the calculator so you get used to doing it. Okay, in this portion, we're going to look at area between curves or some combination of shaded areas. This is a very crude picture. In your notes, you should have 3 really nice drawn graphs that actually work better. So in part, I think it's, what part is it? D. For D, it asks for the area that's inside the cardioid but outside the circle. So it's going to make this crescent moon shape over here. Now in shading that, we want to be careful. So if I draw a line from here to here, that's going to be theta. And then if I come over here, I hit the circle first and then I hit the heart. Same concept, hit the circle first, then the heart, circle, then the heart, circle, then the heart, circle, heart, and I shade. So I'm actually like shading, respecting these segments emanating from the pole or the origin, and then this whole thing ends at this theta here. Okay, so what is that theta? Well, we can say or set the r's equal to each other, and that means where the cosine of theta equals 1/2, and we know that that's going to occur at pi over 3, 5 pi over 3, etc., etc. Now, when we find the area, it's taking the large one minus the small one. The thing is, though, we don't want to rotate from pi over 3 to 5 pi over 3 because that's all this stuff over here. So what we want to do is take it from negative pi over 3 to positive pi over 3, and we have our 1/2. Now it's outer radius minus inner radius. So when we went out, we hit the circle first, and then outer, we hit the heart. So it's going to be 2 plus 2 cosine theta, the heart squared, minus the circle squared, d theta. R squared minus r squared. You can use symmetry and do twice the integral from 0 to pi over 3 also, with the 1/2 yada yada yada, and the 1/2s would cancel out. Last two here. The next one wants to know inside the circle but outside the heart. So let's shade that. I'm going to go from here, dot 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 dot, and shade this. Next angle, dot dot dot, shade this. And that all starts with this theta. And dot 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 dot. We hit the heart, then the circle. Empty space, heart, and then circle. Empty space, heart, circle, heart, circle. No heart, still circle. Same deal. And we go out. We always hit the heart first, then the circle. And that creates this kind of cartoon moon shape. Okay, and this all ends at the theta here. This time, in fact, we will be going from pi over 3 to 5 pi over 3 as we rotate. So this is going to be the integral from pi over 3 to 5 pi over 3, 1/2. The outer radius, in this case the outer radius is 3 squared, minus the inner radius, 2 plus 2 cosine theta, the cardioid, squared d theta. Excellent. All right, last one. Now, in the last one, there are a variety of ways to do this, but I want to show you a way, kind of raw constructing it, that helps you visualize these angles and why it's important to shade in a certain way. This one wants us to find the area inside both, so only the overlapping portion. So that's going to go like this. So we're going to start from the origin. Oopsie. We're going to start from the origin, and we're going to go out to the circle only. No heart, just circle. And go out to the circle. Circle, 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 circle. And then at some point, we stop hitting circle, and then we switch over to solely heart. So it goes heart now. Heart, 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 heart. And it comes in and it's real slow and it hits these hearts. And then finally, we switch back over to the pink color. A little darker, and it starts hitting the circle again. Okay, so you see, we have this theta still, which separates the pink from the blue. In order to find this region, we're going to write it as two separate integrals. So we have the pink, and the pink is going to go from negative pi over 3 to pi over 3, 1/2, and it's only the circle, 3 squared d theta. There are a variety of ways. I mean, you can figure out that sector of the circle with a formula in the beginning, but we're looking at bounds of integration, etc. Now I want to say plus, because now we're going to do the blue. Now blue, the bounds are different, because it's going to go from pi over 3 to 5 pi over 3 to accommodate all the blue, and that respective radius and that respective radius alone is 2 plus 2 cosine theta quantity squared. So the sum of these would give the region of the pink and blue together. There are a variety of ways to do this again. You could find part A, which gave us the area of the whole heart, and then in part, I don't remember, D, perhaps E something, we found this portion, and if we subtract part A from part D, then we would get the same blue-pink region inside there. I'm going to stop there now. That's the calculus portion, area between curves, and dy, dx are the two main things. The homework assignment is in the notes printed at the bottom of that cover sheet from section 10.3. Please have them completed for class. I'll have you know it is 10:13 on Friday night. This is what I do on Friday nights. Loser.